ready to go. So do you have any questions lingering from 2 months ago? Anything that's sticking in your head?
I remember this and how extraordinary that pie chart seems to me.
I know, isn't it? And you can see, that's one of my points.
It's really hard to get your head around.
Yeah, and you can see what's happened. Well, we can go back to this one. You can see what's happened just in a few years from the WMAP to Planck results. You can see how we've even tweaked numbers to be what they are. We did 100 to 400, now we're 300 to 400 million years after the Big Bang for the first stars and stuff like that. So yeah, and in the present day, our understanding is that almost 70% of the energy balance or budget of the universe is dark energy. It's this expanding component to space-time. We still have theories as to what it actually is, and one of the top theories, it is a scalar. So a given spot of space has a given amount of expansion, and that's the same throughout the universe.
And that is the explanation for the observed expansion.
Correct.
And the observed redshifts.
Correct.
We're seeing that.
Yep.
Essentially, it's the creation of dark energy, or the expansion of dark
Expansion of space. Empty space becomes more empty space. It's kind of like rabbits. So you got a Planck volume of space, and in a tick of time, it becomes 2, becomes 4, becomes 8, like that.
And then, I mean, whenever you measure something, there's always some kind of reference against what you're measuring it to.
Mm-hmm.
How do we measure the expansion of space against, if our ruler is expanding at the same time the universe is expanding, how do we measure the
By the redshift of light.
redshift?
Yeah, and it's basically light is having the rug stretched under it as it makes it across vast distances. And since that is consistent, the further out we go, as we use independent distance measurements, then you can put the two together and say, all right, either light gets lazy, which we don't have any other mechanism known to physics that will allow light to get tired, basically, is I think one of the sort of derogatory terms for the other theory, because people don't like it, that space itself is stretching, so it's just having to travel longer, and so the wavelength, as space in the wave is constantly multiplying, the waves end up getting more space in them, which is a lower frequency, which is redder, which is what we see.
Doppler shift, we see that on radio too.
Yep.
When I learned it was, well, just the universe was expanding and this object was actually moving away from us, which would also produce that effect.
Not a constant velocity, though.
Not at a constant velocity.
Yeah, if the velocity is constant, then you're in a reference frame with the source, and so the frequency wouldn't switch. So it takes either, you would get a Doppler shift, but it'd be a constant. Right?
All right, not increasing as you look further.
Correct. That's the deal.
That's the difference.
Yep.
The difference in the observable.
So since you have a steady increase of space, but then as you go looking out further, you're getting more space at a greater distance. It's the same as it just gives a greater redshift with distance, right? But what they're finding here is we knew the universe is expanding, but it's also an acceleration. So it's an accelerated expansion. So the rate of expansion is increasing. So the expansion rate, we're just on the first slide, we're just starting. So we're kind of picking up where we left off last time, even kind of rehashing because it was 2 months ago. But so you have this acceleration, and that's what people didn't expect. So as you look out further, it's not just a constant velocity, it is an accelerating rate.
So this isn't really observable when we look, say, at our galaxy or nearby galaxies.
Correct.
It's too close.
Yeah, even though space is doing what it does down at the smallest scales, thank you, gravity's overcoming that expansion within galaxies, within galaxy clusters, even probably within the filaments between the galaxies. So at this point in time, we expect that to change in the future. Eventually the expansion of space will reach down in and pull galaxy clusters apart, eventually pull galaxies apart. And if the big rip happens, as we'll get to today, it'll eventually pull solar systems apart, stars apart, and molecules apart. I mean, in the end, the universe tears itself apart with this exponential expansion rate of empty space. So, but that we're far from that at this time, and the effects are only seen in the voids between the big clusters of galaxies. And so they're still able to hold each other against it. You know.
So it could, because there isn't the mass, there isn't the observable matter
Right.
to overcome the expansion.
Yep.
So our galaxy sort of behaves as if space really wasn't expanding.
Correct.
Because the gravity overwhelms.
Yep. Even in the scale of tens of millions of light years, gravity can win locally. Yeah. But when you're getting up to hundreds of millions and billions, then...
Did we cover last time? I mean, it's been more than 3 days.
Yeah, okay. No, I've just asked him for questions from last time. So, yeah.
Dark energy is a newer term.
Mm-hmm. Coined in 98, if I recall, yeah. 1998.
And if you can't see it, why do they differentiate between dark matter and dark energy?
Okay. Dark matter, and the term dark has sort of two meanings in astronomy. I'll back up to that. Dark in one case is it doesn't interact directly with electromagnetic radiation. So dark matter is hypothesized matter that we see strong effects from, and I'll talk about what those are in just a second. As dark energy is an effect in empty space that both of them indirectly, by changing the curvature of space-time itself, affect light.
Which we cannot measure.
Oh yeah, we can. Yeah, gravitational lensing, and also the Doppler shift of more and more distant objects.
I'm just wondering if these are things that you have to have, constants that you need to create to answer questions.
The observations of how the universe is working. Yep. And so, so the other part of dark is we just don't know what these are yet. So we're in the dark on what the nature of dark matter and dark energy is. So those are the two meanings there. With dark matter, we see galaxies and their outer reaches rotating too quickly for the observable gas and dust. And so there's more stuff holding them together. And actually, in the case of our galaxy, it's 10 times the size of our galaxy. We see visible galaxies with gravitational lensing occurring with even more distant galaxies and quasars beyond, where the observable gas and dust is not sufficient to explain that much warping of space-time to create the lensing that we see. We see galaxies in clusters that are moving too quickly to remain in orbit around each other if all they had was what we can see. And so they should fly apart with those internal velocities in the clusters. So and then we got things like the bullet cluster. I think I showed a picture much earlier, if not it's coming, of two galaxies that collided, and their visible gas and dust remains are through each other and interacting, coming back. But we can see the warping of more distant objects by this double galaxy beyond the two visible conglomerations of normal matter. And those are the clouds of previously dark matter clouds associated with each galaxy individually. And since they don't interact electromagnetically, there wasn't friction, there wasn't heating, there wasn't a drag on them other than gravity itself. So they've gone beyond, right, the collision. And we see evidence of that in other collisions, not as strongly as that, but that's one of the best examples. So we have lots of indirect measurements of...
An unnamed something at this point.
Correct.
And that's the name they gave it.
And we have theories of like machos, which are massive, compact halo objects. So they could be black holes, they could be lost planets, stellar remains. We can discount those. And WIMPs, which are weakly interacting massive particles. The weakly being the weak force, not that they're weak, because weak force is pretty strong. And that's where we're focused on, is looking for these particles that don't interact with the rest of the universe through electromagnetism, but they may through the weak nuclear force and through the gravitational force. Those are the ways that they plug into reality. And if those are the case, if they touch each other, interact with each other, they are their own antiparticle. We would expect that they would annihilate in interaction with themselves.
That's right, you touched on that before.
Right.
And so wouldn't you think that over enough time they would be gone?
No, because they outweigh even ordinary matter by this amount, and the universe is expanding, so things are going to get further and further and further apart. So the interaction of even normal matter over time is going to become more and more rare in the deep time into the future. So now, oh, whoa, hey.
So this dark matter is different than, you would say, the normal elements that we know of, for example, that don't emit light, because there's iron and carbon.
Correct.
And stuff out there that we probably can't see, because we don't have the methodology to see them.
Correct, there could be, but we should see let's see if I can get a better signal here. The Apple TV has decided not to speak. Let me just reconnect here. I think this is about as far as an Apple TV likes to go. So let me end show. Walk a little closer. Tell it to talk to the Apple TV again. It took away my Apple TV icon. That's not nice. Come on, you. Oh, that's really weird. I might have to quickly reboot here. So what we're looking for when we're looking for dark matter particles is we're setting up experiments where we shield a volume of material from the rest of the universe as much as we can, knowing that dark matter particles can sail right through a planet without any trouble. And if they interact with each other inside of our experiment, then we get a flash of gamma ray radiation. We're looking out in the universe for these flashes, and we're looking inside of tanks of fluid and old gold mines and like that to look for these signatures.
And how do you know that it's gamma rays that are associated?
That is, I think that what they have to do is they have to say, all right, what is the likely mass of these particles? What's a reasonable mass given what we see out in the universe and the warping of space-time? And from that, the amount of energy you'd get out would be equals mc squared. So it would just be the mass of the particle, electron volts, converted over to a frequency. So it'd be, and they have a fairly narrow range that they're interested in. There's this, I don't remember the number, but there's a spike.
So gamma rays fit that.
Correct. Oh, this is really rude. I don't have, it's like Apple TV itself crashed. So let me reboot. And I think I can bring this up on the other computer, and then we won't be interrupted by rude computers.
So is that similar to the arrays that Pablo was working on? Setting up those big tanks, did they measure gamma rays when they came in?
That is possible. I'm not recalling that right now.
Weren't there similar experiments like that to detect neutrinos?
Yep. There you're getting an interaction with the neutrino in the nucleus of the fluid. I don't think they're expecting, well, maybe the fluid, yeah, because they are using what, like, was it xenon or something like that to look for the, oh, come on, computer, just restart. I'm going to take my time, I'm going to ask a whole bunch of questions, I'm going to save a file, I'm going to defragment. Thank you, Apple. And then with dark energy, we don't expect a particle in that case. We expect that to be a part of the nature of space-time itself. It's what empty space does. And we see it by looking at standard candles like supernova across the universe that shine a great distance, but then have a known brightness based on the decay rate of the light that they give off. So we can kind of piece it all together, the brightness as they should be compared to the brightness that we see. And they were actually just looking to see if there was a sign of I think deceleration, like gravity beginning to win the battle against the expansion of the universe, was what the teams were looking for back then. And instead they found an acceleration, which, if I recall the story, a graduate student brought the data to the advisor and said, I get that the universe is expanding. And he went, well, that's ridiculous. Go back and look at your data again. Of course, yeah. My Apple TV built-in function of the operating system crashed. It wasn't a distance thing. So let's hope that doesn't happen again. Well, I'll have to take another big break. I don't want to do that. But when you add it all together, you end up with us missing an awful lot of the story of what is making the universe work.
Which really should be no surprise.
Yeah, so everything that was astronomy before very recently was this. This is what you saw in the nighttime sky. This is what you could easily measure with telescopes. This is indirectly observed by looking at the operation of the universe. Okay, technology, it doesn't.
It's that dark energy.
It is. Okay, stop the silliness here. All right, so any other questions on dark matter, dark energy? Well, we'll touch on them again. So what we see using the WMAP and Planck data is an answer to another question of how curved the universe is. Three-dimensional space-time would have a curvature. That comes from general relativity as well. But the question is, what's the sign of it? And do I have pretty pictures of that? I don't see it. Just like the surface of the Earth, you can have positive curvature, which is spherical, which means if the universe is positively curved, I could theoretically go that direction, super, super, super fast, break the speed of light, and I'd come back and see myself standing there looking the other direction. Theoretically, I mean, speed of light is a very serious limitation to that experiment, like impossible. But in theory, that's what a positively curved universe would give you. Negatively curved is the opposite, sort of saddle-shaped. And the way that you would measure that would be, say, put big lasers out in space and make a triangle, and then measure the angles on the inside. So the angles if you draw the straight lines, geodesics, on the Earth, you end up with angles wider than 180 degrees added together. And if it's saddle-shaped, then they curve inward, and so you end up with angles a little bit less. They add up to less than 180 degrees on the inside. If it's flat, then you get your nice Euclidean geometry of 180 degrees inside of a triangle. The area inside of a circle on a sphere, because the sphere bulges up out, is greater than what you would get from pi r squared. And on a saddle, it curves down in and is missing, so you get less area than you would expect. But what we see looking at that data of the cosmic microwave background radiation is that it is so close to flat that we really can't, it's within the air of our determination to say one way or the other, if it's a little positive or a little negative. We're very close to flat, which implies that the universe is nearly infinite. All right, so let's crawl through the Big Bang here, and we can speculate as to what might have come before the Big Bang, but you're really reaching beyond observational limits at this point. Now, if we can get neutrino astronomy to the point we can start peering back to the earlier moments of the Big Bang, or if we can start to look at gravitational waves from rebounding throughout the universe left over from the Big Bang, we might be able to make something a little more informed about what came before, if anything. Of course, the nature of time becomes pretty hinky when you go back to a singularity, if that's what was at the Big Bang. But was it another universe? Did we have a big bounce? Was there a collapsing universe before ours? Ours we do not expect to ever turn around and collapse and bounce. So we're in an unusually different universe from whatever came before, if that's the case. is our universe somehow finite but unbounded in time? Is, like I said last time, if there's a membrane nature to the universe with higher dimensional membranes wandering around, and we're just stuck on this three-dimensional membrane here, and another one touches this one, you could fill the entire universe with energy that would expand away very quickly, and it would give all the, or not all of it, but many of the similar signals of a Big Bang, but space wasn't a point initially. Everything ignited, filled with energy, and then spread out, cooled, and stars formed and like that. So we don't know. We can speculate, we can make models, but we don't know. So the best model, or the one that assumes the least, is you had nothing at first. Then you had a quantum fluctuation of some type in a almost incomprehensibly different space or time type mixture. Who knows? But once that happened, there was stuff. There was the beginning of a space-time here. And that first 10 millionth of a second, the temperatures of the universe were about 1 trillion degrees. We can even calculate a density, 10 to the 13th grams per cubic centimeter. You had no matter at this time, you just had energy. So it's way too hot for any subatomic particles to exist. In this point, as matter and antimatter began to cool out, just in the few instances after this, matter won over antimatter by a small margin, a ratio of 1 billion to 1. So we're left today with a lot of energy and some leftover matter. It's the rounding error in this initial state. Why this is an area of research. We're looking at the laws of quantum mechanics to try to look for asymmetries that explain why what we call matter, or what the physical stuff that the universe is made of, has cooled out and left this matter for us to become what we are. And there's some leads on it, but I'm not going to go too deep.
When you're going from temperatures that hot and cooling down from when energy can form matter, it could form antimatter or regular matter.
Correct.
Almost equally.
Yeah. In the first glance, we don't see a strong reason why it's not just equal. And then the universe would have been just gamma ray radiation at first that would have cooled down to microwave. It would have been a big black body bubble that nothing happened inside. Yeah.
Does antimatter have the opposite polar charge as regular matter, like with electrons?
Right, electrons are positive charge and the protons have a negative, antiprotons are negative charge. Yeah. So it is an electromagnetic switch. Yeah. Like once they touch, they just completely unwind, and you have a complete conversion of the matter into energy, equals mc squared again.
And that's been done quite regularly.
Oh yeah. Yeah, we can generate antimatter at will. It is the standard byproduct of a number of subatomic reactions.
You just have to find it.
Yeah, what is it? Dan Brown, and was it Angels and Demons, or was it the original Da Vinci Code? I didn't read either one, but one of them has to do with stealing antimatter to make an antimatter bomb. I think that was. The flaw in the book is that if you looked at all of the antimatter that humanity has ever made so far, I believe it's much, like a tiny fraction of a paperclip worth, not a large quantity. So we haven't made, we're not going to do the Starship Enterprise with our matter-antimatter engines and like that. It's just That we know of, okay, yeah. Well, whatever Skunkworks is doing.
Yes.
Yeah. Okay, edit that part out, please. All right. But we know that by 4 seconds after the Big Bang, the universe is cooled enough that all protons and neutrons are made. So quarks exist, and electrons exist, and quarks, there was probably a quark soup early on, but as soon as temperatures dropped, quarks had to be hidden away from us inside of protons and neutrons. So it takes 3 quarks each to make them. These are composite particles. After 2 minutes, it's cool enough for deuterium to form. So now a neutron can stick to a proton to make that form of hydrogen, or be pushed into it at least. Because deuterium is 2, tritium is 2 neutrons and 1 proton inside the helium. And again, just reviewing all the way back, an element gets its name by the number of protons it has. Everything else can come and go. Neutrons can be added and subtracted, and those are isotopes. Electrons can come and go, and those are ions.
I have a question about the 4-second level.
Mm-hmm.
You didn't put electrons there, but you said it.
Yeah.
Did they necessarily form at the same time?
Earlier. Electrons and quarks all came out of this early super hot phase. I just don't have that level of detail here.
At that point, the universe was charged? Because if there's all these electrons and no protons.
Yeah, you're going to have a net zero charge. So, because the quarks do have charge.
Quarks have charge?
Yeah.
A fraction of the charge, though, right? A third?
Right, correct. Very good. You're on top of things.
I should remember the rule of threes.
Absolutely. So at this point, nuclear reactions are occurring throughout the volume of the universe. And so this is the same physics that's going on inside of stars, minus the heavier elements that play around in here. And so we can now get helium formed. The universe is expanding very rapidly. And at 30 minutes, anything that expands cools, be it hairspray or air coming out of a bicycle tire or the universe, it cools. And it cools to the point where the nuclear reactions shut down. And if you run the math, you find out the percentage of hydrogen, helium, and lithium that you would expect during that time is what the universe is populated with as the base level. Yeah. And then somewhere around 400,000 years, the universe is dominated by bright radiation. It's so hot and dense that photons can't go very far before getting reabsorbed into the next bit of matter. And then just like the surface of the sun, remember you could fly right above, if you could stand the heat, you could fly right above the surface of the sun, or go all the way down to 10% into the radius of the sun, and that's at the point where you have 1 Earth atmosphere. So below the photosphere is a great deal distance in, you're at 1 Earth atmosphere. So the photosphere, the visible surface of the sun, is sort of an illusion. It's still very close to a vacuum. It's just the point where the matter cools enough that photons can fly free and make a big leap all the way to other stars and planets and light us up and give us an image of a sun's surface. So just like that, the universe has a surface back in time, and that's the cosmic microwave background radiation glow that I showed 2 months ago, the baby picture of the universe. So the universe becomes transparent, and that's what our spacecraft and microwave telescopes see as the 2.725 Kelvin background radiation glow. That's pretty low resolution, so. But I guess we can get some of the big points. So you have the Big Bang here. This is 1 Planck time unit. And then you have at this point, grand unification, where the electromagnetic strong and weak nuclear forces all act like one force. Then at this point forward, the strong nuclear force becomes its own thing. Here, the electroweak is still, electromagnetism and the weak nuclear force are still acting like one, and they separate. Here you get nucleosynthesis, 1 second, 10 days, and going out hundreds of thousands of years to millions of years, you get the first galaxy. So atoms are right in there, solar system forms. So this is a big logarithmic scale to zip through the first fraction of a second. So this is all 1 second right down in here.
What's kind of temperatures can we create experimentally? Obviously, very small areas.
Very small. I think we're back in this area. I don't think we've.
Explosions.
Yeah, because we can
undo that anyway.
Yeah, we can play with nucleosynthesis left and right. So yeah, and you can fuse and you can break apart atomic nuclei. We do that. So, but we don't have the ability to make temperatures where we see electromagnetism and weak look like one. I'm sure of that. But we've done it mathematically. So
Somewhere in the 10 to 11 kilokelvin.
yeah, yep. So our options on the critical density idea was, is the universe closed and coming back, or open and going on? With no gravity, it would just sail on forever. But we now know that the universe is going to keep expanding unless some new phenomena emerges in the distant future. One of the things I wonder about, and I actually haven't seen in the literature much, but might there be a time where electromagnetism separate? I mean, these are all separating out. Is there a point where the universe cools enough that electricity and magnetism become separate forces? Hasn't happened yet, obviously. They're intimately linked together, even if they act differently.
Is it related to zero-point energy of alien bays?
In a way, it might be. It might be. But we have gotten temperatures in lab experiments down extremely low, and I don't think we've ever seen that phenomena happen. So, I don't know. If it happened, it'd be like Ghostbusters. All matter flies apart at the speed of light, and total protonic reversal, right? Yeah. That's not a scientific term. So presently, we have these numbers for the dark matter, visible, and dark energy budget. So, trying to refine the Big Bang Theory, some of the early problems were the flatness problem. How do you get a universe that is this flat in such a short period of time? And one of the ways that we know that the universe has something unusual going on with it is how similar the cosmic microwave background radiation is from that side of the universe to that side of the universe. That is similar to looking at quasars. We saw these brilliant, unbelievably bright beacons, tremendously redshifted, that were changing in brightness in hours and days. So you know an entire galaxy can't altogether change its brightness in hours and days, because it takes tens of thousands or hundreds of thousands of years for information to travel across an entire galaxy. So you can't get a whole galaxy to coordinate its brightness because of the speed of light.
Why would it have to travel across? Why would it have to travel across? You mentioned the membrane before, if the entire outside,
Yeah, well, yeah.
you know,
Mhm.
was one, it would essentially all be the same thing. It wouldn't be.
Correct, but with quasars, we see quasars in all different directions. They're all doing their own thing.
Yes.
Yeah. So the idea is that it's probably something very small that's making that much brightness, because then all its parts can be coordinated together. So yeah, now with the membrane idea, that does also solve the flatness problem, but the membrane is much more speculative. It's kind of an offshoot of string theory, and you've taken a lot of assumptive leaps at that point. So this is more the mainstream solution to it, which has also got some assumptions.
At one point, thought the Earth was the center of the universe.
Yeah, that's true. So with quasars, what we now know is the brightness comes from the region right around a massive black hole. It's very small, with a lot of material falling in. It's an active galactic nuclei, and this stuff gets processed in that small, violent, high temperature environment. You're getting this beacon of light that can change very quickly. So the same with the universe. So for everything to be so similar all the way around the universe, something like outside membrane doing everything at once, or everything being in close contact when it mattered, and then frozen that way from then on without the ability to change much,
Would
had to
that be
happen.
the same kind of thing as, and I don't remember the details, where they've got two, and I don't remember if they were protons or electrons or whatever, but they do something to separate them.
Entanglement.
Entanglement.
Yep,
And then
okay.
they act as one,
They do, correct.
even though they're separated.
Correct. Problem with entanglement in this case is entanglement happens when you don't have the system disturbed, and this is an unbelievably high temperature, high density environment where everything is disturbing everything. So
Right.
yeah, entanglement wouldn't.
But it can happen in these circumstances, so why assume it can't happen in those circumstances?
It's a good question. Let me think about that. I'll put that right over in this part of the brain. I'll let that grind for a little bit. Well, the solution that's been mainstream for a while is the inflationary period, that really soon on here, in the first tiny fraction of a second before the forces start breaking apart or anything, you have something that makes the universe expand really fast. So way back here, you got inflation. So actually they have it in this one, they have it at the point that the grand unification theory happens. Gravity is an outlier, and it's its own weird little thing. We're still looking for evidence of gravitons. By looking at, I did my, the section earlier on black holes, and we're doing the experiment now. We're trying to image our central galaxy's black hole environment to actually make an image of the event horizon. Look at light coming past it to look for anomalies in what we'd expect. We're also looking at, I think we went through this before too, is it M87? There's another galaxy with a much larger black hole in our sky. The angle that it subtends is big enough that we can also probably image its event horizon. So we're looking for anomalies that help us get some idea of what's going on with gravity and the forces back here. So at the point that the electroweak splits out of the strong, period of inflation begins, 10 to the minus 36 seconds. So back here, we kind of think of the universe as maybe having one single super force. Somebody can name your kid if you ever want. Super force, yeah. And so there we go with the 0 point energy, that in cosmology, vacuum energy is taken to be the origin of the cosmological constant, possibly dark energy. That this energy that is sort of a false bottom right here is where you're getting this expansion from. And in one way, to look at it is that the entire universe's energy budget, dark energy, dark matter, and normal matter, and electromagnetism, light, and all that, are a big bank loan from gravity initially. So gravity is the lender, and we're in the hole owing gravity for all the energy that we have. And that was the mechanism of the Big Bang itself. Because you can't get something for nothing. So it all go back to this creation time. And so we have this 0 point energy in the vacuum also is related to the virtual particles that we see that spring out of nothing. And thanks to Heisenberg's uncertainty principle, they can, the particle and antiparticle that are created out of nothing, rejoin again before we can measure them. We you don't get to see them, but they pop out long enough to affect space and time and help build reality, basically. We do see their effect, as I say, with the Casimir effect, that do I have a picture of the Casimir effect? I think I talked about it before. That the Casimir effect is, in a really good vacuum, you take two plates, and they're really perfectly flat plates, and you allow them to get closer and closer and closer and closer together. And you get them close enough that these virtual particles don't have room to pop and then reunite in the direction of the two plates. They can still do their little pop into existence and vanish hiding game in the plane of the gap. On the outside of the two plates, they're doing it in every possible direction. And so as you get the plates really close together, and this is just a tabletop lab, it's expensive, but it doesn't require a gigantic thing, you get a net inward force. You get a push from these virtual particles on the outside. These are the same virtual particles that pop into existence. One gets sucked in and one gets away from the event horizon of a black hole, and that's Hawking radiation. And that's the ultimate demise of black holes, will be that negative influx of energy into black holes, giving them an effective temperature, a very, very low temperature, much lower than the temperature of the universe today. So all black holes are still eating, even completely isolated, they're eating black body radiation from the Big Bang. But eventually, the universe, as it expands and accelerates in expansion, temperature will drop down below the temperature of the smaller black holes first, and eventually drop below the temperature of the bigger black holes. Bigger is cooler. So what we see now, in putting this all together, is we don't really know what happened at the point of the Big Bang. We call that the Planck era, where you're in areas smaller than the Planck. A Planck scale, let's see if I can do that, it's 10 to the minus, 10 to the minus 35 meters, I think, is the Planck scale. And as you, okay, let's say you want to image, one way to define this is we want to image a building. You can use radio waves and get a rough idea of where a building is. If you use microwaves, you'll get a fuzzy picture of the building. If you use visible light, so higher energy light, you get a really sharp picture of a building. If you go down to like a little grain of sand and try to detect one grain of sand with radio waves, you're going to have a horrible time. It's just too small. But switch to higher energy light, then you can get a good picture of a grain of sand with visible light. Go down to a molecule, and radio is not going to work, light's not going to work. But if you go to higher energy X-rays, say, you can get really good images of what's going on inside of a crystal for X-ray imaging. It will give you actual lattice structure of a crystal. And so as you get smaller and smaller, you have to use higher and higher energy light to get the wavelength down to where it's comparable to the object that you're trying to observe. As you go mathematically down to, say, trying to get an image of a proton or image of smaller particles, eventually, if you want to get down to the Planck scale, the photon has so much energy that it turns into a black hole for an instant. So that's the limit. The 10 to the minus 35 meters, you can't go any further. You've pumped so much energy, theoretically, into your observation that you've now created something that can't be observed for that instance. So it's the floor of the spatial extent.
So because the photon destroys what you're trying to image?
That's a side effect of it, but in this case, there's just so much energy in a small space that it collapses. Now, the Hawking radiation temperature of a black hole at the size of the Planck scale is so high that it instantly decays. You get your light back out again right away in 10 to the minus 43rd seconds. Yeah, 10 to the minus 43rd seconds. So you only get a black hole for 10 to the minus 43rd seconds, but you do. So this is thought to be the shortest tick of the clock of the universe and the smallest scale or volume of the universe. So we are interested, when we're dealing with the entropy of a black hole, in how many Planck areas fit on the event horizon of the black hole. It's the ultimate measuring stick of an extreme phenomena. So after that, you get the elementary particles, possibly, where quarks and electrons, the constituent particles of the later composites like neutrons and protons come into existence. We're not really sure. And then you have the inflationary period. The universe expands much faster than the speed of light. Again, space can expand faster than the speed of light. Just things can't move around in reference to anything else faster than the speed of light by you accelerating it, or if the speed of light is the speed limit of stuff, not empty space. And the universe cools, you get particles, antimatter was common back here, antimatter becomes rare, nucleosynthesis ends, you have nuclei here, the universe cools, that's the wall that we see using microwave and visible and everything else, normal telescopes. Then you've got a bunch of neutral hydrogen and helium, and then the first stars start turning on and ionizing the universe, and the universe then starts cooling out to form galaxies and clusters of galaxies and so forth. So, quick picture, there's the cosmic microwave background radiation. Here's the point of inflation, where the universe, in essence, heads towards infinity in size because of the flatness that we observe. It's hard to put an infinity on a PowerPoint slide. So, yeah, I already covered that. So the Planck area is 0 up to 10 to the minus 43 seconds. All the forces are 1. We really don't understand physics of these temperatures and pressures and this close to the singularity. Time is going to be weird, because remember, when you get a lot of stuff in one place, time doesn't run. So from our point of view, time was nearly stationary back in these times, which is a weird way to talk. Then expansion, cooling, you got the first force, gravity froze out, the electric weak epoch, Strong force freezes out from the rest. We don't have the math yet for this either or here. Then the inflationary period, again, we have a theoretical inflaton field with particles called inflatons. They're driving the universe to a fantastic increase, 10 to the 26 times larger than it was. The volume increases by 10 to the 78 power. Then you get more matter made than antimatter, and we still don't have that explained. We have leads towards it. We get supersymmetry breaking, which is speculative at this point. And then electroweak breaks out, the quark epoch begins, and now we're in hadrons with protons and neutrons forming. So we are still pushing hard into all this unknown. I had 2 slides of a lot of unknown here. It's frustrating, but it's also job security. So 1 second to 10 seconds, new electrons and other electrons are no longer made. So all that happened in that first second. And then photons dominate from 10 seconds to about 375,000 years, bouncing from particle to particle. The universe is cloudy, opaque, and hot and bright. And then in 3 minutes to 20-minute area, hydrogen and helium are made. And then matter domination up to 70,000 years.
I have a question.
Yes.
Like, at those temperatures, were the nuclear reaction rates still the same as we observe today?
Yeah.
Because
Yeah.
their fusion rates.
Yeah, even in the, early on it would have acted like the largest stars present, and then as it cooled, it would have been like the smaller, lower temperature stars. Yeah. So then from somewhere around 375,000 years, the universe becomes transparent. We have the dark ages up to 150 million years or so. The universe is foggy to some frequencies of light, but it's dark. The first stars have not formed yet. Then the first stars form, you get reionization, lasts for maybe 1 billion years, and the first stars start clearing out this universal fog, and you get formation of galaxies from 1 billion years to present. Our galaxy got going about 4.9 billion years after birth, after Bang, 8.8 billion years ago. You get the formation of groups of clusters and superclusters at about the 1 to 2 billion year point after the Big Bang. And it's still happening today. Our solar system forms about 9 billion years after the Big Bang, 4.6 billion years ago. And we're in the habitable epoch. Stretches from 375 to present. So could there be earlier civilizations that got their act together before us? Maybe. That'll be what we talk about in the next whole section after we're done with this one. And now we can go to the future, see how this ends. This is the habitable epoch, the end of the solar system. Probably about 5 billion years from now. I don't know why it says 1. Well, I think the idea is that it's possible that the orbits will become unstable. There's some models say that we're in a temporarily unstable or stable period, but eventually the sun will swell and swallow Mercury, Venus, and maybe the Earth. That's still debated. 5.5 billion years from now, the Andromeda and Milky Way galaxies will merge. And then the Big Rip, if that is the correct model of the future, will occur just beyond 20 billion years from now. Here on Earth, I can point out that about 1 billion years from now, we believe that the core of the Earth will cool enough that plate tectonics will cease. So weathering will dominate the effects on the surface, wearing down the continents pretty quickly, and we'll be in Kevin Costner's Waterworld. So we won't have any land. We'll just have water all around until it starts to boil off later.
Even Pike speak? Even Pike speak?
Yeah. Yes, probably. Yeah. If the Big Rip isn't the future, the Big Freeze, where the universe expands to the point that it's so cold, stars burn out, that's about 100,000 billion years from now. Heat death, where entropy completely wins. Black holes have evaporated, given up their energy, and very possibly protons may spontaneously decay. They kind of tunnel out and then dissipate. 10 to the 1,000 years from now, the universe is really done. No more time ticks forward even. And then does the vacuum itself, that's now exponentially increasing in size, running away, become destable and cease to exist? That would be even a more distant future. So there's lots of ways to die in the universe. All right. So let's get into theories of everything and see what we're doing to solve some of these problems. What we need is to solve this big question, to figure out what is going on in the earlier instances of the Big Bang from the Planck time up to the first second, and what is going to be the ultimate fate of all those different fates of the universe. And to do that, we need to tackle why general relativity and quantum mechanics don't get along. They don't play nicely in black holes, they don't play nicely at the Big Bang, they don't play nicely if you go all the way down inside of atoms and try. We don't even put gravity in nuclear reactions. It's feeble as all get out, but in situations like this with the black hole, it now matters. Feeble becomes strong enough to matter. And part of it is the singularity. Do we have singularities, and what is a singularity, and what's going on around it? What's happening on the event horizon of the black hole? What's going on inside the black hole? So we'll talk about that after a break. We started late, so I went a little longer past the hour. We'll do maybe a 5-minute break and pick it up from here. All right, so let's do a quick refresh on black holes, take a look at how these two don't get together. And then what we're going to do is transition into large chunks of my theory of everything talk, which is the first talk I gave at the LTO. So you're going to get a rehash of parts of that with all that we've taken up to now. And that probably we're not going to get through that today. So we'll pick it up again in September. So I'm talking about large numbers on Friday night in September here, using the Library of Babel as an example. So yeah, it's going to be fun. And we get to actually visit the library while we're here. I'll take the whole audience to the library. We'll read books from the Library of Babel. So, and we're going to talk about some of these numbers, these giant numbers of the death of the universe, and like we'll play with those in comparison to the library. So it's really just a vehicle to try to visualize vast numbers. So and I did learn, spoiler, there's a number called Graham's number. It's really interesting. You should look up Graham's number. There's no way to express the size of Graham's number inside the universe. You don't have enough Planck areas, volumes through the universe to even write the digits of it, but it's not infinite. It's a finite number. Crazy. So we'll talk about fun stuff like that in September, and then we'll pick it up here, wherever we are in the next morning. So refresh of Einstein with gravity, a way to visualize it, since we have difficulty visualizing volumes that change their nature three-dimensionally. It's simpler to look at gravitational sources and black holes and like that in a model of a two-dimensional universe. In fact, that it often helps in these cases to drop a dimension and you can visualize it and then kind of let part of your brain extrapolate that up as to what that might mean in the real world around us. So you get the rubber sheet model and you have a gravitational body, something with mass and energy sitting down here in the bottom, which we don't draw because it blocks our view. And you can see as things travel in straight lines through space-time, they either curve, you can go in an orbit around it, or they can go in orbit out and way down in and back out. So kind of interesting way to look at orbits. So around the sun today, you've got a surface. You don't want to go flying into it because it's too hot, but out here you're just going on around. And of course the question that I always give my astronomy classes is what would happen to Earth's orbit if I pushed my nefarious bad guy button here and turned the sun into a black hole? And the answer is nothing, right? You have the same curvature with the same mass here. It would be a black hole, so it would stretch down like this, but out here it would look the same. So it just gets really cold here. Like, so the forecast is for 400 degrees Fahrenheit below tomorrow, and the next day, and the next day, and the next day. So around a compressed white dwarf, you have a much more sharp gravitational well down here. So you still don't want to be playing around with white dwarfs when you get your spaceship from the dealership, because I'm sure that voids the warranty.
So going from the sun to a black hole would not change things as much as going from the current sun to having it turned into a white dwarf.
No, out here it'd still be the same.
It would still be the same.
Yeah, at a distance, because when you're looking at when you're looking at a gravitational source, it works perfectly well already to do the math as if all the mass was at a point in the center.
Oh, okay.
Now, what you get with an extended object like the moon, you can see a half degree across the sky, or the sun if you're getting too close, is you get tidal effects. So you get differential gravitational effects that stretch and pull and change stuff. So it's a point source plus tidal effects based on its extent across your view, from your point of view.
Which is not what you think of as tides on this Earth, because
Right.
that's moving the ocean.
Right, but it is. I mean, the atmosphere rises and sinks, the Earth's crust rises and sinks daily. Yep. Twice a day. So when we go looking at space-time, again, we're looking at the stretched rubber mat back here, and divide it up, and then start getting down, magnifying spots, magnifying spots, magnifying spots. When we get down here and look at the math, where you're approaching the Planck scale of reality, see, you didn't think Planck scale would be that important, and it's coming up all the time now. That things go crazy. The mathematics describes this foamy, jittery, chaotic space-time down here. And that's got space ripped around and breaking and foaming, and you got time forward and backward, and it's just nuts. So from Einstein, we get special relativity, that all velocity is relative. Space and time are both aspects of the same thing. Accelerational pull and gravitational pull are indistinguishable. That's the general theory. Energy and matter are the same, equals mc squared. And space-time curvature is energy. It figures into superstring theory. And general relativity and quantum mechanics just don't mix when we get all the way down inside the atom. So what to do about it? So let's transitioning over. This is kind of our philosophical guidepost. We'll go to Stephen Hawking saying, if we do discover complete theory, it should be in time understandable, in broad principle by everyone. And then we shall, all philosophers, scientists, and disoriented people, be able to take part in the discussion of why we in the universe exist. Brian Greene says no matter how hard you try to teach your cat general relativity, you're going to fail. So, and then, but Brian Greene does say, we can certainly go further than cats, but why should it be that our brains are somehow so suited to the universe that our brains will be able to understand the deepest workings? Well, we're going to try. We do try to make sense of the world around us. We're actually going to go all the way back to the beginning of the course, briefly here. We like linking previous ideas to new ideas. We make categories of everything. Like green things growing outside. If you look at every single green thing individually, you get trillions of green things. You'd have to come up with a name for every blade of grass just in front of the LTO. But if you start to categorize in your trees, bushes, grass, moss, you're under 500,000. And if you figure out types of chlorophyll, you're down to just 6 chlorophyll containing plants types. So, and then if you bring in evolution and genetic tree of life, it all comes from one original eukaryotic cell. So simplification, simplification, unification is what we're always trying to do. Myths try to have an all-encompassing explanatory power. They have a breadth, where science tries to create explanations. It gives you both breadth and depth. Breadth links many phenomena at once, like all the different green plants, where depth, we try to explain and predict in a way that all independent observers can do the same. So different cultures, different languages, different ages, different background scientists can all look at this reality and come up with the same explanation of how we got to this moment in time and explain and predict where things are going to go.
But either one, you're leaving out one of the really important things about the human brain or human beings is once we've decided we've got an answer, we don't want to have to change that.
Well, that's true, but that's what science hopefully does is transcends that.
Hopefully.
Yeah, it's very much like evolution. In fact, it progresses very similarly. It goes down dead ends, it tries different things, but the winning idea is the one that explains and predicts the best. And even if a century or two has to go by with bad ideas dominating, eventually, as observations get better, as people can make a name for themselves if they tear down the old and create new, someone comes along and starts to chip into the wall. It was Lord Kelvin famously in 1899 meeting, I think of the, I don't remember the organizational meeting, it's just not coming to me right now. I might have a quote from him actually. So that pretty much all science is now determined. We just have a few loose ends to tie up or something like that.
They almost closed the patent office at one point.
Oh, yeah.
Because they assumed everything that could be invented happened.
Yeah, well, now that we have an iPhone, it is done, right?
Oh.
So we've had lots of theories of everything. Myth today now means untrue, but that's sort of a morphing of the original term. So it's a traditional story accepting history, serves to explain the worldview of a people, sometimes including the origin. So, let's see what I see. So I don't remember this quote. So the human imagination has seldom had before an object so sublimely ordered as the medieval cosmos. If it has an aesthetic fault, it is perhaps for us who have known romanticism a shade too ordered. For all of its vast spaces, it might be in the end afflict us with the kind of claustrophobia. Is there nowhere any vagueness, no undiscovered byways, no twilight? Can we never really get out the doors? Okay, that's cool. So to start to piece together the universe, and we're going to go right up to almost, as some philosophers of science say, when you're dealing with string theory, you're beginning to kiss myth, that you're going to the point where in some avenues of speculation, it seems there may never be a way to test it. If you can't test it, if you can't come up with a way to break your theory, is it science anymore, or have you left that realm? But we'll get there. We seem to be wired to expect there's a reason behind everything, that there is cause and effect. And it's this chain of cause and effect that lets us reach back to the very early instances of the Big Bang, and then drag our minds off into the distance of heat death in the future. Of course, in the pre-Copernican astronomy, we had astrology and astronomical observations made by many regions in the East. Aristotle came up with his concept, it's a philosophy more than a science, that's all based on perfection. And even with Brian Greene, we've got The Elegant Universe, is his big book in Nova series. This elegance, this order, or as Carl Sagan put it, this cosmos, which is an order in the universe, is an underlying assumption. But if we don't make that assumption, we can't make these leaps back into the past and out into the future and take the theories we have much farther than observation allows. Those assumptions of the earth was changeable and I'm imperfect, but the heavens are perfect, unchangeable, came with the ideas of these crystalline spheres. You didn't see any parallax as you moved around in a field, so maybe it's probably a bowl-shaped sky with everything out there on that last heavenly sphere. We know 4 forces, and those weren't even imagined then: the gravity, electromagnetism, the strong and weak nuclear forces. And what we're going to try to do is unify these into one. That's the goal. In fact, these are graphics from Brian Greene's video. With gravity, we see Copernicus making the first link between the gravity that's obvious to my legs right now and the heavens. He came up with a heliocentric model, or sun-centered model. I wrote it down, the De Revolutionibus, finished in 1530. Explained planetary motions without epicycles, which is, as we said in the history of astronomy, it was an important breakthrough, because doing this little fix of perfect spheres and perfect circles, you had to put in other little perfect circles in there to explain why planets seem to go backwards. But it still wasn't really perfect, because he still assumed circular models. They're really ellipses, as we'll see, but that was one step too far. Tycho Brahe measured the positions and planets of the stars, saw a supernova, which kind of broke that perfect universe idea. He didn't see parallax in the stars, including that supernova, but did measure 777 star positions and planetary positions almost daily for 20 years. Cloudy skies, of course, get in the way, and birthday parties probably too. He hired the mathematician, that should be a singular, to work out the orbit, and he came across Kepler. Kepler was early on really stuck on this famous idea of these perfect solids, explaining the motions of planets and lots of other things in life. Built models of them and was trying to extrapolate to all aspects of spiritual and physical well-being, and then began to work on the math of Tycho's observations. Tycho died, he ran off with the books. Family pursued him for a long time. I guess you just couldn't copy a PDF document back then. So, no scanners. Take a picture with his phone. But when he came along with the idea of ellipses, planets move faster when they're near the sun, came up with the laws of planetary motion, almost was just a few steps away mathematically from writing down the laws of mutual gravitation that Newton did later. He abandoned this old stuff. He was, as you said, able to drop the idea that he was so passionate about and move on with this mathematical thing. To my knowledge, he never returned to try to get ellipses working into that or anything. I think he was mature enough to let that go, as Elsa would say. So we get Kepler's 3 laws. Ellipses solve the motion problem, so now you don't need any little epicycle fixes in the perfection of circular orbits. At foci, semi-major axes, eccentricity is what you need to describe things going around things in curved space-time. You have the equal area and equal time law, and in years, p squared equals a cubed, being the period and the semi-major axis of the orbit. We didn't know why things moved. So we come along with Newton. We're now into the 1700s. And he was really a Renaissance man with interest in everything. He invented differential calculus, got the nature of gravity, 3 laws of motion. He made big strides in the understanding and mathematical description of optical systems, like stud. So from Newton's 3 laws, we get a body, our mass continues at rest, uniform motion unless acted upon by an outside force, which is a big leap because we don't see that in day-to-day life. And if I push this little adapter, it comes to a stop. That's obvious, but that's not. This is a frictiony world dominated by gravity, pushing things together, making them rub against each other, and that gives us this counterintuitive discovery. But it was critical, because then you can take friction out and treat it as its own force. Famous F equals ma that solves tremendous number of problems. One body exerts a force on the second body exerts equal and opposite force back for law 3. Newton's laws of gravity, published 1687. Very simple. You got the 2 masses, distance between them squared, gravitational constant, attractive force, so it's negative. And voila, now he had an expression of the force and how it decreases with distance, explains the speeds of planets around each other. Pretty incredibly fantastic and elegant. That's really short. There were failed earlier attempts at explaining gravity and all the other forces, being that there's some mysterious superforce when this force with distance alters. So when it's below, it acts attractive like it's attractive, below the line it attracts, so it acts like gravity far away. But then you get repulsion in some other intermediate distances inside an atom, say. Doesn't work, but it was a good try, Boscovich. These other forces, we see electricity. Static electricity is known to the Greeks, 600 BC, Chinese in 270 BC. We knew of this phenomenon of electric eels. 1752, Benjamin Franklin's kite idea. To the best of my knowledge, he never actually flew the kite. Other people did and died. So we had Franklin live a long life because he probably didn't actually do it himself. Magnetism, Greeks write about it 500 BC. Chinese were finding lodestone and making compasses back 100 AD. You can use stuff engineering fashion without knowing the science behind them, and they did. James Clerk Maxwell came along in the late 1800s and unified electricity and magnetism into electromagnetism, published 1873. You have one force with the photon being the particle that carries the force. Of course, you have an electromagnetic field too, fields and forces, and particles are all interchangeable, and that goes back to E equals mc squared again. So looking at the overall time, have you guys seen this talk? Have you been through this before? This is okay, so I'll take my time with it then. So looking at the overall time, a lot of amazing things happening here. We have Copernicus coming out of the 1500s here. Got Luther doing his stuff, Michelangelo painting here, Leonardo da Vinci, and Columbus is sailing the Atlantic. Then we enter what we call the 99 years of astronomy, where astronomy really gets born. So got Copernicus putting out his idea here, and then Tycho's observations, Kepler takes over, and laws 1 and 2 and law 3 come out 1609, 1619 respectively. Telescope is invented. Galileo's come along here, and he starts to observe, not inventing the telescope, that was Holland, I think, but he was using one. I think he improved it a little bit. Wrote his dialogues on 2 worldviews. Was imprisoned after that. We have Shakespeare writing at this time, Elizabeth I, Milton, Bacon, Guy Fawkes, Rembrandt at the end of this period. Newton right after this period. You got gravity being expressed. You got William Penn. Blackbeard is doing his stuff. After this, we have Bach, Voltaire, Mozart, Beethoven, Benjamin Franklin's life here. There's the kite idea. Boscovich is right in there. French Indian War, George III. There's George Washington. Go see Hamilton if you want to see this part expanded upon. Napoleon right there. So, pretty crazy time there from 1500 to 1800. So gravity, going further, Albert Einstein, coming out of the 1800s, going into the early 1900s. As a teenager, wondered what it would look like if light would look like if you tried to catch up with light. And so he was all into trains. So if you had a train going at the speed of light and turn on the light in the front, would it pool up in a bubble and dribble around the sides of the train? Would it just not be able to leave the light and build up? What would happen? So that's what I was wondering about as a teenager. He gives us the mass-energy relationship, E equals mc squared, only using simple geometry and algebra. He pounded math into himself as his life went on, and he also hired and associated himself with mathematicians who helped him at different stages throughout. I came up with special relativity first. It says that time slows and space shrinks at high velocity, and general relativity, which says time slows, space shrinks in high gravity, and time and space are one entity that warp with gravity. As we will see, warping of space-time also can contain gravity, contain energy as well. And he worked on unifying electromagnetism and general relativity to the day he died. He launched quantum mechanics by solving the ultraviolet catastrophe problem, basically explaining photovoltaic properties of some metals and why they don't produce infinite energy if you put them out in the sun, which they don't, obviously. And that quantized concept of light helped get quantum mechanics going, but he hated it. He hated the probabilistic nature of quantum mechanics. And the answer to his teenage question, I don't think there's a slide coming up about this, because we're kind of going lightly through this, comes from the speed of light being a constant in vacuum. So when the train's going at the speed of light, if it could, and you turn on the headlight, it's not speed of light plus speed of light, it's just leaves at the speed of light. And what gives, what because something has to give, is that time is slowing for the train and space is shrinking for the train. Train is foreshortening to theoretically 0 at the speed of light in the direction it's traveling, and time stops for the train. So from an outside point of view, the light goes on, heads off at the speed of light. To the point of view of the person on the train, the light heads out at the speed of light. So the point of view problem is maintained, but this is what gives in its place. But again, that is a big mental leap. That is taking an idea, again, kind of like Newton's first law. It's taking an idea and just saying, this is what works. I don't necessarily have a gut feeling of how that happens, but this is what works, and I'm going with it. And it's that willingness to just take a step out onto what seems absolutely ridiculous and going with it that the big breakthroughs in science seem to come from. So, Greek philosophers created the concept of an atom being indivisible. Atoms were first detected in the late 1700s to the 1800s. Einstein kind of solved that problem too, 1705, by describing Brownian motion. So he had his fingers into lots of stuff too. He's like Newton, he didn't stay just in his lane. The nucleus of the atom was finally detected in 1909, which kind of ruins the original definition of the atom as being indivisible, but oh well, those poor Greeks. And then we get in 1913 the Bohr model of the atom, which is very much like a little solar system. Before that, they didn't know what was inside of an atom. Was it like a fig pudding with little figs inside, or what? But the nucleus there, they would send electrons through. Sometimes it would bounce off. Sometimes, was it right? No, neutrons. What would they send through? I'm blanking on that because electron would interact with the atom. So I think probably neutrons. But anyways, they're sending other particles through and determined it wasn't just a random distribution inside, that there's something really small and dense, and the rest of it's pretty much empty space.
X-rays.
Is it X-rays? That, I guess that could make sense in the 1913 area, 1910s. I'm gonna have to look back at that. So every once in a while I have to question myself and then I wonder. We get the quantum physics model of the atom in 1924 with orbitals and a much more complex structure of how atoms and electrons are constructed and interact. The weak nuclear force was quantified in 1965, the year I was born. It was suspected back in the 30s. Its most visible effect is radioactivity, where the photon is the force-carrying particle of electromagnetism. You have the W and the Z bosons. We have two force particles. They are photons, that should be an N right there. They are the equivalent of a photon for electromagnetism, the W and Z boson. So you can get field, particles, interchangeable, just different ways to look at the same phenomena. Strong nuclear force, suspected in the 20s, but finally quantified in 1975. I was around doing stuff in 1975, and they figured out this is really recent. That's really recent, both of these. It's not that far back. When you look at dark energy, 1998, I mean, that's really recent stuff. We are in the very birth of a lot of this science, and it's pretty exciting. Can certainly use the nuclear force to make the nuclear bombs of World War II, but we didn't really know what was going on. There were some scientists back before the first nuclear bomb was detonated at White Sands were afraid that once it went off, it would ignite the entire planet's atmosphere and sterilize Earth, ending all life. But no, we're still here. This holds the protons and neutrons together in the nucleus. The gluon is the force particle of the strong nuclear force. And the gluon, if I remember correctly, is where most of the mass of the neutron and proton come from. Einstein didn't accept the theory of quantum physics. It started appearing in the 20s. So as he was hammering away at unifying electromagnetism and gravity and electromagnetism, thinking another thought, he was missing half of these forces that we now work with. So he didn't have a hope of doing it, but he had a notepad on his bed, working on it right to the end. So we found the theory that links electromagnetism to the weak nuclear force and expressed that in 1974. So the standard model of quantum physics is born. Our grand unification theory is where we want to link the electroweak force with the strong force. And I can change that to an 8. So it's still in progress in 2000. I guess it's been a while since I taught this. I need an editor. So what we're hoping to do is start to figure out some of the parameters of the high energy subatomic universe, to start getting a mathematical hold on how these forces may actually be unified. So the Large Hadron Collider takes these proton beams, opposite directions, very high energy collision, you get very short-lived particles, massive detectors in multiple spots around the ring, all looking for the energy budget of these collisions, looking for the things that come out. And the analogy is taking a pickup truck and a semi-truck, or two pickup trucks, and smashing them together as hard as you can. The pieces fly a half a mile in every direction, and then you look at the pieces, you keep doing that until you have a full understanding of what makes pickups. So, of course, the concern early on, kind of like the ignition of the first nuclear bomb, there was some concern that this would create little mini black holes, and the little black holes would fall down out of the machine, unseen, down to the center of the Earth and meet each other and start gobbling up material and start growing, and eventually the Earth would collapse down into a black hole. So, problems with that concern are these black holes would be very tiny, very high Hawking radiation temperature. They would decay very quickly. We also have particles coming in from space, cosmic rays, highly accelerated protons that smash into our atmosphere with energies much higher in individual collisions than we can generate here. So we have already had black holes raining down on us since the moment the Earth formed. These little black hole creations, if they could occur, would also be occurring on the surface of neutron stars. And they would react much quicker because they're almost there to a black hole. And so if that could happen and the cosmic rays could trigger black hole creation, then we wouldn't have any neutron stars. All neutron stars would be tipped over into black holeness. So they're pretty confident that things are okay. And we've been running it for years now, and things are okay. Energies go as high as 14 tera electron volts. The frequency, remember I said higher and higher frequency light is needed to probe smaller and smaller. So the frequency of the gamma ray equivalent of light energy being used in here is 10 to the minus 19 meters for the wavelength. So that's a really high energy reaction going on. Ultra high vacuum, very low temperature inside, 1.6 Kelvin. And what we're trying to do is look for the Higgs particle, which we have, 2015. That was announced with high confidence. They now have they have found it, yep. Announced July 4th. I was camping and I got a little pop-up on my phone. I'm dancing all over the campground. They got it, they got the Higgs particle. It's good. So we can talk about Higgs a little bit later in more detail, but have I talked with you about Higgs? Okay. Of course, we want to try to unify these forces. We want to see where the strong nuclear force joins the electroweak to give us the grand unification theory. We're trying to see if we see things that are generated that could be dark matter candidates. Is there unobserved missing mass? So let's say you smash these pickups together 1,000, a million, a billion times, but you never see the steering wheel. Like, how does this work without a steering wheel? Steering wheels are probably there, but steering wheels make up dark matter. So I don't know how far I can push this analogy. Okay, I'm trying. And we're looking for matter-antimatter asymmetries that hopefully we'll be able to, as we get higher and higher energies, again see a tilt towards the matter and why. So we can answer that early question in the formation of the universe. We know it happened because we're here. Right? And I had one student ask, well, what if the universe is actually made of antimatter? Wouldn't we call it matter? I said, well, of course, because matter is easier to say than antimatter. So it doesn't matter which way. All right, so we piecing it all together, we had the concept of electricity, magnetism, and light. Those were unified into electromagnetism. We have beta decay, which is radioactivity, and neutrinos, and those were linked into the weak interaction, weak force. These two were linked together. You can see that happened in the 1800s, that happened in 65 and 71. They were linked, electroweak interaction. We knew of protons, neutrons, pions, mesons, things like that, all the little particle zoo. Able to link those together with a strong interaction in 73. Electroweak and strong came together uneasily right now for the standard model of quantum mechanics. Earth's gravity and celestial mechanics are linked into universal gravitation with Newton in the 1600s. Geometry of space-time was brought in by Einstein, linked to that to create general relativity. And now we're trying to get these two to work together. The idea is simplify, unify, bring it all together into one big story. So, looking at it from the force point of view, the force carriers are gluons for the strong force, the W and Z bosons for the weak force, photons for electromagnetism, and gravitons, you see no hint of them, to make gravity. We see strong force creating quantum chromodynamics is the explanatory mathematics. The weak and electromagnetism come together in quantum electrodynamics. Those together with quantum chromodynamics create the electroweak theory, and then hopefully we get the grand unified theory to put those together. And someday we'll get quantum gravity, which we don't have. We want to bring quantum gravity into the grand unification theory to get the theory of everything. So there's a lot of work to be done on this lower right side of the force carrier thing. So back here, we got particles, here we got forces. So what does a good theory of everything create? Well, unifying forces. Yes, we'll explain the origin of the universe. It'll help. We'll explain life on Earth indirectly. We'll explain why we're here. No, that's a lot more work to be done there. We'll explain why I had eggs and toast this morning for breakfast. No. So we find the Higgs particle and we're done. No. So I'll be working on the largest and small subject in the universe, superclusters and neutrinos. I'd like you to handle everything in between. All right. So we'll pick up next month with a little review through those particles and forces and theories. We'll get into the deep problem of why these don't get along and start to play with, there's the spherical, saddle-shaped and flat universe and the triangles. We'll get right back to the baby pictures of the universe and start going forward into quantum mechanics and how it all relates and doesn't relate in our understanding. So, bring questions. Thank you, everybody.